This is a video for AQA Further Pure Mathematics, Algebra and Graphs section 3.7, where we're looking at sketching polar curves. We should note that first of all you'll be asked to sketch curves rather than to find an exact graph. Now you can do this by plotting a few points, but the idea is not to plot several points. So a few and then connecting together gives you a good idea of what the graph might look like. You should also think about how the value of r changes for different values of theta. Particularly you might look at where theta is equal to 0 or is a maximum or a minimum. These are often involving trig functions, sine and cosine, and so these vary between -1 and 1. It's also possible, if you have one available, to use a graphic calculator to plot the graph and then copy your sketch from it. However, that does take a bit of practice, so if you're thinking of doing that, I would recommend that you try several examples to make sure that you can use your graphics calculator efficiently. Well, for the rest of this video I'm going to look at 4 examples of polar curves. These are listed here: r equal to 4, theta equal to pi by 4, r equal to 2, and then bracket 1 plus cos theta, and r equals 4 sine 3 theta. So you'll notice first of all the first two only involve one of the variables r and theta, whereas the second two involve r and theta in both equations. Let's take these then one at a time. So we'll start off with the first one there, r is equal to 4. Well, if we think about that, what's happening here is that the value of the radius that's coming out from the origin here is always equal to 4. So we could plot some points, but they're always going to be at a distance 4 from the origin. So if I go around just putting a few of them in at 4, then it doesn't matter which direction the radial arm is pointing in, the distance from the center is equal to 4, and of course you can see that these lie around a circle radius 4. So for different values of r then, all that would happen is that the radius of that circle increases or decreases. In the second example, it's theta that isn't changing. So that means that we're always going to be pointing in one particular direction. In this case, the direction where the angle is pi by 4 from the initial line. So if we come round from the initial line here, a value of theta equal to pi by 4, then the line is going to come out, or there's going to be a line pointing out in this direction. So it doesn't matter what the value of r is, it's always in this direction away from the initial point, the pole. Notice that it goes in that direction only. So it's not the same as having a line which goes from -infinity to infinity. This starts at the pole and heads out in what in effect is a northeasterly direction on our graph. Now for different values of theta, of course, all that would happen is that ray that's going out from the pole would be pointing in different directions. So for example, we could have theta equal to 3 pi over 2, and that would be a straight line coming down in this direction here. When it comes to graphs like this one, where r and theta are connected by some equation, then it may be worth plotting a few points, although I wouldn't advise doing all of the points here. I've got a table set out with values of theta in fractions of pi from 0 up to 2 pi. Cos theta, of course, it starts off equal to 1 when it's 0, and then goes to reduces down to -1, and then goes up to a 1 again. So starting at 0, then our values are 1. At pi over 6, actually root 3 over 2, or 0.87, 0.866. I'll write in some others. At a third pi, it's come down to a half, and then down to 0. But we could start plotting values then with 3 plus 1 plus cos theta, 3 multiplied by 1 plus cos theta, sorry. So this would start off at being equal to 6. 1 plus 1 is 2, so 3 times 2 is 6. And by the time we get down to pi by 2, it's reduced to 3. So if we now put that onto our graph, we're starting off at a value at 6, and it's reduced to 3 by the time we're pointing in the direction of pi by 2, which is up there. So we've reached this point here. Now that's happened slowly. It's reduced down at a half at pi by 3. Now pi by 3 is the second line going through there. So we've reached 4.5 at that value there. And so you can see that what's happening is we're starting off large at 6 and then gradually reducing. So what happens after that is that we're going to reach -1 by the time we get to pi, and therefore this will have reached 0. And then things start increasing again. So we're going to have smaller values now of cosine theta, reaching 0 by the time we get to 3 pi by 2, so then we'll have come back out to 3. And then finally getting to 1 at 2 pi, so we've come back to the value at 6. So it's actually a reflection of that top part of the graph in this sort of fashion, coming around here. There's the full value, and there's our graph plotted fully on a nice display. Well, I can show that happening on a GeoGebra graph. Here we've got r is equal to a times b plus cos theta, and c is the angle. So at the moment starting off at 0, but if I increase c, you will see then that the line comes out as we described before, reaching 3 when I've got to there at 1.65, so pi by 2, and then into 0 and back out again, producing that curve, nice looking curve. It's actually called a cardioid because of the shape of the curve. But I can also look at this and vary the values of a and b. So b is the value which is being added to cos theta. So let's look at that varying and see what happens if I increase it. Well, you'll see that the shape gets larger, becoming more circular in effect. That's because the value of b is taking over from the value of cosine theta and becomes more dominant in the equation. If I go the other way, then you'll see that the curve actually goes into the negative part of the graph. That's because b plus cos theta becomes negative. And then we're back to the one that we started with. Changing the value of a, on the other hand, leaves our curve looking the same shape, just increases its size. So that's an enlargement scale factor going on there, increasing the value. The final graph I want to look at is r is equal to 4 sine 3 theta. So notice it's 3 theta here, therefore it's going to be changing rather more rapidly than a sine curve. Sine theta goes 0 to 1 and then to 0 again in a distance of pi on the graph. So with sine 3 theta, that's going to happen between 0 and pi by 3. So in fact our values of sine 3 theta are going to be 0, 1, 0, negative 1, 0, 1, 0, etc. So changing between 0, 1 and negative 1. So if we look at what happens on the graph, 4 times that, so obviously going to be 0, 4, 0, negative 4. So let's consider that on our graph then to start off with. Starting at the origin, the pole, when we've got 3 theta equal to 0, and then by pi by 6, which is going out in this direction, it's reached a maximum value of 4, so we get to here. But then comes back to 0. And then what's going to happen now is it becomes negative. So when we reach the direction of pi by 2, which is up there, it actually becomes negative 4, which is down here. And then back to the origin, and then finally when we get to a value of 7 pi by 6, we've got negative 1. So negative 4 for our distance, but where's 7 pi by 6? Well, that's down in this direction. So negative 4 is actually going to produce the same point as here. So the graph actually completes itself and then repeats what's already gone on. Perhaps a lot easier if I look at this on a GeoGebra file. So here's the file. Again, I can change the value of C. So increasing C, and you're starting off at 0. It's going to happen there. It is going out to the value of 4. And then by the time we get to 0 again, that was at a value of a third pi. It became 0. And now it's gone in the negative part of the graph. So there we have just past there pi by 2, so that the graph, instead of going up in the direction pi by 2, is coming down to this point here at negative 4. Continues getting smaller again as we increase. And there we are, we've got to pi now, and we've repeated, we've got the whole graph there. So once we get past pi, all that happens is that it goes round the graph again. I can look at what happens for different values of A and B. Well, A, first of all, you probably guess that what happens with A is that that's an enlargement scale factor, so all that happens is that the petals, if you can call them that, get larger. But B, interestingly, this changes how quickly we get round that full circle. So if I change the value of B, let's say down to 2, see we've now got 4 petals. If I come down to 1, it's just a single 1. So that the value of theta really looks at whether we get repetitions as well in the graph. There we are. There we've got round there to C is equal to 10, and it's still not completed the full pattern. You might like to think about why that is and how many petals would you achieve on that. So let's just reset it for the one that we started with, where A was equal to 4. And B was equal to 3. I'll just show it happening again then. So increasing to 4, down to 0, and then into the negative part. And finally round and finishing when we've got 2, theta is equal to pi. That completes this video about curve sketching, and indeed completes the section of videos on Algebra and Graphs 3.